Hello. Hello, welcome to the webinar with Felix Wick, Dr. Felix Wick, by the way, but we can go on to this a little later. The intro was in French, don't worry, we will speak English solely. We can switch a little bit to German, but let's stay on English. Welcome to the webinar with Felix Wick with the title Gen AI and Classical ML. When to use what? To our speaker, who is Felix. He is Chief Data Scientist, Executive Data Scientist at Panasonic Research and Development Center, Germany. And he's Director of Intelligent Systems Laboratory of Panasonic Connect. So we will look at the question, how is generative AI different from classic machine learning? When would you use the one or the other? Can they be combined to get the best of both worlds? And what has all this to do with deep learning again? So this are the questions we will follow very much. You are always invited to post your questions in the chat. They will be answered as actually Felix decides, or I would say, if you don't mind, at the end of the webinar. We ourselves, we wait a little bit until everybody is on line. We are data scientists. We are a teaching institution for data sciences. We give seminars or courses on machine learning engineering, analytics engineering, data engineer, cloud engineer, and all that. If you wish, of course, you can get in touch with us. We are data scientists, and I will leave the stage to you, Felix.
Okay. Hi, everyone. So nice that I'm here. Thank you. Yeah, so we can, of course, ask in between all the time, right? So please make it interactive. So whenever you have a question, so it's a relatively broad field, and I have many details and topics to talk about. But yeah, I think it's best if you just ask so that we don't get lost in the middle. And yeah, so in French, will be a little difficult. So I live near to France, but my French is pretty poor, so better to do it in English, I guess. Okay, so then I guess we are good to start, everybody here. So then I would say, yeah, let's start with the slides. So let me see. So you can see it, I hope. Yeah, so I will directly get into it. So yeah, so we already had in the introduction what I will be talking about. So as I said, so this is a super broad field because it basically covers all of the current landscape of machine learning or AI, if you want to call it like that. And this is here a brief teaser, so to say, about the topics some of them we will touch a little deeper. Some of them we only scratch the surface, but in principle, in the current situation, you can actually distinguish all the applications that you have with machine learning in these two fields, generative and predictive models to some degree. And still there is lots of classic machine learning that I will tell you a little bit what I mean by it, and deep learning applications. And yeah, as I said, so those are some examples. So there are many more applications, and we will talk about a few. But for some of them, you see what it is, right? So, for example, the text generation case that you have with ChatGPT and all the language models. So this is clearly a deep learning application with the transformer architecture behind it. And it's also a generative model because it creates text, right? So on the other hand, there are also large language models like the famous BERT family from the former Google search stuff. So that came a little before the chat applications. So these although still deep learning applications, this would be rather predictive models. And on the computer vision side, a little bit more. So these are also deep learning models, mainly convolutional neural networks, but also predictive ones, right? But things like text to video or text to images, so image synthesis and such things, these would be generative models again, right? And classic tabular data, this is still with classic machine learning models like XGBoost, so tree-based approaches, and it's also predictive models. So as I said, we will go through it one by one, and this is basically the idea of the topic of today. Okay, so let's start with what deep learning is and what foundation models are, because this is the backbone behind all of the applications that you see at the moment, especially in terms of language models and so on. Okay, so let's start slow. And for all of you, or for most of you, I guess this is more repetition. But the classic supervised learning setup is actually something where you have, let's say, a tabular data set. For example, you have different emails that you want to classify into spam or not spam. So you basically want to do an input-output mapping. So your output is a label, spam or not spam, and your input is, for example, the words in an email. And so you have a very specific model for each task and data set in the classic setup. So that means a spam filter would be a very specific model. Another task like predicting the price of a house would be another model. Okay. And what you do on the way for this input-output mapping is actually you need to do some kind of feature engineering usually. That means you cannot just use the input data directly, like the raw words in an email, but you somehow need to process it to make it usable for such an input-output mapping. So in this example here, this could be the occurrence of specific words or the length of an email or something like that. In another setting, like what I said with the house prices, it might be you have some raw information about the condition of the house and you somehow process it in a way that it's directly usable in your model. So this can come in many forms. So another example would be if you have the date, you would kind of transform it in the day of the week, the season, and so on, right? So this is basically the idea. So there are plenty of such classic machine learning use cases. So I said a prediction of house prices, but there can be so many things like the energy consumption prediction or demand forecasting is very important in industry, or churn prediction for telecommunications provider or whatever, right? So all of these things are predictive models. So that means no generative AI behind. We have this input-output mapping. We take all the inputs that we have, so all the columns, let's say in an Excel sheet or a CSV file, that we have as features, and one specific column is our output column. So this is the target that we want to predict. And we kind of find the statistical dependencies between those in the training and apply them in the prediction. So this is the classic setup. So I assume that most of you know. And all of what comes on top basically works in similar terms, right? But it gets more complicated. So what is now the transition to deep learning? So it's basically this feature engineering that I explained that we want to replace. So let's start with this, I call it here ladder of generalization. So if you think of it, look from the left to right in the sketch on the right. So you have this rule-based system. So this is the super classical programming. So that means you have some input, you do some hand-designed algorithm. So really an algorithm that takes the input and creates an output, right? So there is no learning. There's just a deterministic input to output mapping in a sense of a rule-based system, if you want. So classic machine learning now does this mapping from features to output by learning. So that means you have some parameters in the model that you would actually tune by means of data. So this you don't have in the rule-based systems, right? So there you would basically set the parameters manually. So think of a linear regression. You would basically set the slope and the intercept manually. In a classic machine learning sense, you would actually adjust these parameters by means of data. So that means this is the machine learning setup, and this mapping from features is where the magic in the learning happens. But still, the features would be hand designed by means of this feature engineering that I mentioned. So, and if we now come to deep learning, so then the situation changes in a sense that you want to extend this mapping now also to the creation of features. So that means you want to use the raw data itself and let the deep learning approach kind of shape the data a little bit so that this feature engineering is done automatically and not manually anymore. So this is a huge step because it would make things much more general. And yeah, it's just much less work, right? So, and much less complicated than if you have to do this manually. So, and by doing so, you also hope that you can learn hierarchy of concepts, right? So this is the depth in it. So you add many layers, and you hope that with deeper layers, the concepts that are learned get more abstract. So think of, for example, computer vision of the face recognition, so to say, as one example. So you would start with some very basic things like an edge detection or something like that. And then later on in later layers, you would detect a nose, an ear, and so on, and eventually a full face. So, and with a classic approach, you would have this edge detections kind of as feature engineering that you have manually worked out, right? So you would manually write an edge detector, and then eventually you would have machine learning to do from your, let's say, from all your features that you have engineered to the final output. So that's, for example, to say, so this is Felix, something like that, right? So this is the idea. So if you want, what deep learning does is it basically takes the raw data and somehow shapes it so that eventually it can be easily used for a final classification, for example. Okay, so this is now the distinction between what I would call classic machine learning, like tree-based approaches or something like that, or support vector machines or whatever, towards the really modern applications of deep learning, right? So now there is a slight issue with it. It sounds like you should always use deep learning and everything is shiny, but this is only partly true. So for unstructured data, so which is, for example, images or text or video or something like that, this works really well. So there usually deep learning is the model of choice, and you don't have to think about the classic machine learning applications. The reason for it is that this data is very homogeneous. So if you think of my example of the tables where you have the different columns, so here each of the columns, for example, would be a pixel or would be a word or something like that, depending on what you want to do. So, and all of the pixels are basically the same things, right? But for structured data, so tabular data, so there the different columns can mean very different things. So they are very heterogeneous. So for example, one might be the condition of the house, the other thing might be the square meters of it, and so on, right? So that these things can mean completely different things. So, and such heterogeneous data is much more difficult to be used in deep learning directly. So that means usually what you need to do here is you need to do some feature engineering yourself, because the model would have difficulties to do this in a feature learning setup. So that means to some degree, deep learning loses its advantage in those applications. So, and this is the reason why simpler models like gradient boosting are still used a lot here. So first, they have less difficulties to deal with such structures, and also if you would use it with a deep learning approach, you would still have to do the feature engineering to some degree. So that means it wouldn't really help a lot. So this is the reason why for this tabular data world, you still see many models that are not using deep learning. Okay. So, and we will come to it in the end a little bit again. But for now, I will turn the attention a bit more towards those foundation models that are used nowadays in computer vision and natural language processing, because they are the backbone of all the fancy applications that we see at the moment, especially in terms of language models. So What is the idea of transfer learning? So the underlying idea is that you have a generic so-called pre-training step that you do on huge data sets, right? So this somebody does once, and then if you come to some specific application or a specific task, you don't have to go through all the learning process again, but you can do a very lightweight learning on top, which is called fine-tuning, which is done on a much smaller data set. So this is a huge step forward, because if you have such models available, so and with model I mean not the source code itself, but basically the outcome of the source code with data. So really the trained model, so the final algorithm, if you want, that you can directly apply. If you have them available and can just fine tuning smaller data sets, this would be a very, very generic approach. So this is of course very helpful because it spares you lots of work, right? And lots of compute, especially. And usually this is done with deep learning methods. The reason is that their compositional nature, so of neural networks that are behind it, allows it to do this very easily, this fine tuning. So basically adding additional layers or changing the weights of some layers and so on. That means deep learning methods are really very great for this kind of foundation model. And yeah, so this also explains why it's so successful for unstructured data like computer vision, object classification, or language models that we will touch later on. But yeah, it also means that for tabular data, usually foundation models are not that helpful. So that means there you usually have to train the different models from scratch all the time. Which is not that cool, right? So this is also in industry still something. So you need lots of data scientists who do lots of specific modeling for specific tasks and cannot really use foundation models a lot for those. So there are actually some promising researches for some edges where one comes closer to a foundation model. So for example, if you look at univariate time series, there are few applications where you actually can do some foundation model, but in general for tabular data, this is still something that is very challenging. So there is work that is being done at the moment in research in this, but I guess it will take some more years until we see this really applied to many business cases. Okay, so now I mentioned computer vision and language models, so I will touch it briefly. So as I said, I cannot go to details here, but only that you know what I mean. So for computer vision, we are mainly talking about convolutional neural networks still. Okay, it could also be vision transformers, but in many applications, it's still convolutional neural networks. The reason is that there is some specific inductive bias in images, and this is locality, right? So this is how the physics world work. And the convolutions actually have this inductive bias directly baked in, while a transformer would have to learn it to some degree, right? So that means it makes some sense that you still use CNNs for this application. But anyway, how does it work? So you usually pre-train it on a large data set. So for example, ImageNet, right? So the very famous one where it all started with deep learning with AlexNet. So you train it, for example, on object classification. In this case here, you would have 1,000 different classes that you want to classify. And then you could actually apply such a model. So that means the trained models with all the weights and everything, you could apply it to a different task. So let's say you want to classify now 45 different objects, right? There are different possibilities what you could do. So either you just fine tune all the weights, right? Or you only fine tune the last layers if you want. So the dense layers after you flattened from the two-dimensional world used in the convolutions and the pooling into the fully connected layer to do the final output. But yeah, all of them basically share the same idea. So that means you have learned all these fancy features, right? So like our reality looks like in the pre-training, and the fine-tuning then only has to do the lightweight classification, so to say, for your specific case. So that means you don't have to repeat all the learning process about the features that you are going to use, right? So this is the idea behind it. So this is the classic fine-tuning approach, if you want, in computer vision. So then, of course, there are plenty of use cases in computer vision, right? So it's not only the object classification, it's also detection, it's image segmentation, it's tracking, right? And you can do all different kinds of things with it, like defect detection. I already mentioned face recognition, autonomous driving, also lots of medical imaging. All these things are applications with these models as backbone, so to say. But again, these are not generative models. We are still in the world of predictive models here. Okay, so aspects of it. So the models can be actually used in generative applications, which we will look at later on. But still, those itself would be predictive tasks. Okay, now I mentioned language models, so let's also briefly look at that. We will come back to it later and later again. So what's the analog of language models when we compare it to the features that I mentioned that were abstracted in the convolutional neural networks of computer vision? So here it would be something like contextual semantics, right? So first place, what is the semantic itself? So semantics would be actually done in terms of vector embeddings in language models. So that means if you think of the classic or not classic, it's relatively new, but the self-supervised learning setup that you do. So you basically have a large text corpus and you go over it with a sliding window of some context size. So let's say 10 words or something like that, right? You always mask one word and predict the next one or one in between, depending on the architecture. And this is the setup that you learn from, right? And you basically chunk the text into, you split the text into chunks, like words or tokens, actually more technical. And the first thing that you need to do is for each of those words, which is basically just one word out of a huge vocabulary, like a one-hot vector, right? You need to give it semantic meaning because itself has no meaning yet, right? If it's just a category in a huge set of a vocabulary. And you do this by transforming it to a dense vector, right? So this is the idea of vector embeddings. Again, I cannot go into details now, but yeah, probably you already know it. You can either do it in a dedicated approach, like word2vec, or you do it end-to-end in a transformer if you want to do, for example, text generation. And this then possesses a semantic meaning in the sense that the similarity, so if vectors are close to each other, so let's say if the dot product between them is large, so that means those words would somehow mean a similar thing, right? So let's say you have 10 dimensions of such a vector embedding. So each of the dimensions has some kind of semantic meaning, right? So you could somehow think of it like that. But with the plain embedding approach, like in word2vec or in the back of words approach, it's just the semantic meaning of the word itself. You don't have included the meaning that it might have in different contexts. So let's say if it now comes in one text or another, it might mean different things, right? So for example, I eat a green apple or I have a cool apple product can be two very different things, right? So that means the context itself is also important. And to actually include the context, you need something like either recurrent neural networks, right, or the self-attention mechanism that is used in transformers, right? So if you apply this, again, this is kind of a dot product approach. I don't go into details of attention, but you basically see the idea in the sketch on the bottom of the slide. It gives you in the end now a contextual embedding. So that means all what happens if you flow a text or words through such a full language model is in the end you get out a vector representation with a semantic meaning that is aware of the context it comes in, right? So this is basically the features, if you want, that the language models learn. So what it outputs in its last hidden layer, so to say, before the language model had. I come to the details later on, how you would use it, but this is kind of the features, if you want, that the language model learns. Contextual semantics. Okay, so now what you do with it. So you can actually, as I said, we have done self-supervised pre-training on massive data sets, right? So this is the foundation models like GPT or BERT. What we want to do with fine-tuning is, again, we do some specific data sets now, and we adapt parameters or add layers. Same thing, right? So the first approach that would be predictive is if you want to do something like a sequence classification. So this is the classic approach with things like BERT, right? So encoder models. Again, I will come to it in a second. But this basically means you take these contextual embeddings and you now train something like a small language head on top that gives you in the end as output, for example, a sentiment analysis, whether a text was good or bad or whatever, right? So something like that. So this would be a predictive application of such a pre-trained language model. Generative application, you already know, I assume. So these are the things like ChatGPT and so on. So usually they are also fine-tuned afterwards. You would call this instruction tuning. So you might be aware of this reinforcement learning from human feedback, for example, that is used in ChatGPT, or there are also other approaches. Also, supervised fine-tuning is used in such an alignment process, if you want. And this is instruction tuning that you do here is also a type of fine-tuning. And the fine-tuning itself is predictive, right? So basically, you present the language model some examples in the supervised fine-tuning that you wanted to predict like that. But the output of such a language model would be generative. And I come now to the distinction technically what predictive and generative means. So this is kind of the mass description of it, right? So a predictive or discriminative model would usually predict a conditional probability. So that means you input the features, the columns that you have, so to say, in the classic setup of tables would be the X, right? And the Y would be the column that you want to predict, the target, right? Or in the computer vision sense, the Y would be cat or dog, and the X would be the pixels, whatever. So this is what you do. You have, if you want to now predict a new data point, you have the X and you want to predict the Y, right? So this is the approach in predictive models. So where generative models model the joint probability. If you want to think of targets and inputs, it's Y and X. Usually it's more like X only in the unsupervised or self-supervised setting of texts or so. So you basically predict the data points, the data generating process itself, right? In the predictive model, you would not predict the X. You take them as given. So here you predict the input, so to say, yourself. So if you do so, this allows to generate new samples. So this is pretty cool. So you basically generate new words when you do text generation, right? But it's also more difficult, right? So a discriminative or predictive model only has to distinguish. So it takes features and distinguish things of it. So this is what we said, for example, in the object detect or object classification case, right? Whereas a generative model would now have to understand all aspects of the input. So to generate a new input. So that means generate a new image is very different to just classify objects on an image, right? So this is way more difficult. So now generative models, if you can actually predict the joint probability, you can also use them to do conditional probabilities, so to say predictive tasks, just by using Bayes' theorem. But the point is, usually predictive models are better at predictive tasks than generative models, just because they are dedicatedly trained for it, right? So that means usually if you have a predictive task, and you would better use a predictive model itself. Okay, so now let's go in some details that and some examples that are already mentioned. So text generation. So, language models, this we already discussed, we generate the next word, right? So this would be decoder LLMs. I will show in the next slide the thing, what is the difference between an encoder and a decoder. And another example is image synthesis. So these are usually diffusion models. Again, we will look at it in a second. So here you would generate new images, right? So usually by means of giving it a prompt, right? So and these are currently the two dominant approaches, I would say, for generative AI. So the two main applications. So for the image synthesis, take care that you not confuse it with the multimodal understanding in LLMs, where you basically just give it an input and an image as input that is now again splitted into patches and tokenized, so to say. It's a different thing than generating a new image, right? So this is something that one should not confuse. But now let's look quickly encoder, decoder LLMs. So what's the difference? So I already mentioned GPT-BERT as the examples. So in an encoder, in the pre-training, you have a masked word prediction and you look at both sides of the word, right? So you just mask a word in the middle of a sentence or of a context window, and you predict it from its surroundings. So to generate this contextual embeddings. While in a decoder LLM, you do a masking in a way that you only predict the next word, so to say. So you basically only look at the past when you predict the next one. So that means there in your context, you go over it and always only use the words or tokens that come before the one that you want to predict. So this is just a different setting. And usually you would, as we said, the fine tuning would work for the encoder ones. You would really fine tune it on the downstream tasks to apply it, right? So because the contextual embeddings itself would not really do anything. While the other one, you already do in the pre-training, the next word prediction, you only do this instruction tuning, so to say, to get it work. So the difference between both in application, so it sounds very similar, right? But in application, there is quite a difference because the encoder ones, so they usually rely on a fine tuning to be useful, right? You cannot generate text, you cannot prompt them, right? While the decoder ones, so these are really generative models. So there you generate the next word, so to say. And you do this, if you do this in an auto-regressive manner, you can come up with something like a chatbot, right? And you can also do question answering and so on by giving it a hot start with a prompt, right? This would be something like that you use in prompt engineering, right? So either zero shot, so that means you just ask a question without giving any examples, or few shot means you give it some examples how you want the machine to answer, something like that, right? So that means here you really have the setup that you can be very generic in terms of giving prompts and let the thing generate new words. So this is basically the difference between the two of them. So one is predictive, the other one is generative, if you want. And yeah, so this text generation thing, so the in-context learning that I mentioned with the, for example, few-shot examples or prompt engineering. So this is really, of course, a new paradigm, right? So this is changing the game a little bit because now you don't have to write dedicated models again for some things, but you actually can let the machine do a completely new task, right? So just by means of giving the information in the prompt. So this is kind of, if you want, attention to the context. So this is, of course, very interesting because this enabling of multitasking capabilities overcome this kind of limitation of all of machine learning before, that it was only used for narrow tasks. Right, so that means this is of course now a setup. So, but that would allow you to go beyond the classic modeling of individual tasks for each of your cases, right? So, text generation is let's say the prime example of generative models at the moment. Yeah, maybe a little bit of history. So, as a small detour here. So, if you think of usage of compute of different models or foundation models, if you want, that were trained over the last years. You see that some years ago it was mainly computer vision, right? So like convolutional neural networks that I mentioned, AlexNet started it, ResNet and so on came afterwards using skip connections. And then at some point the language models came in, like the original GPT and BERT. And of course, nowadays we are already much further. So with much more compute and with GPT-4 and so on, and Llama 3 as kind of the state-of-the-art open source model at the moment. And in between, we have a few reinforcement learning algorithms that we will have a short look at in the end. So like AlphaGo and so on. But it changed a little bit towards language models now. And the reason is why they are so interesting nowadays is exactly this in-context learning, making it multitasking, right? Still, the numbers that you see here, so they are very impressive. And one thing that is quite interesting is they do a lot of memorizing, right? So that means there is not real genuine understanding so much, but still lots of memorizing that anyway makes this this very impressive capabilities possible that they do at the moment. Okay, so now briefly to image synthesis. I already said it. So the idea here is that we generate images from variations of images in a training data set, right? We don't copy them directly, which would be an autoencoder if you want, but we slightly twist them, right? So that means we learn something like a variational distribution in the latent space, and then we use this to spit out images that are similar to the images in the training data set, but slightly twisted, right? And the point is that usually this is done conditioned by some text prompt. Otherwise, it wouldn't be useful, right? So if you would just do some arbitrary variations of a training set, you could not do a lot with it. But if you can now condition it on a prompt, give it a text, so to say, what you should generate, and you generate a new image, this is, of course, a very cool application. And of course, this would be a generative one, right? The thing is that usually compared to text generation, this is slightly more complicated because here you have more complex structures, right? So like in images, if you want, the structures are more complicated than the sequential structures of relatively deterministic language. So that means here you cannot just use the plain transformer architecture usually, but you want to or you need to use some additional mechanism like diffusion or something on top. But if you do that, of course, there are plenty of applications, right? So it's not only text to images, it can also be text to speech, whereas this are, of course, rather translations if you want. But it can also be text to video, right? So these are very cool applications that came up quite recently. And they are, of course, so interesting because they allow to do some dynamics or physics understanding, right? And yeah, you know all the famous applications that you can play with. And yeah, maybe at some point, such generative models might also be capable of coming up with some generation of new proteins or materials or whatever, right? So this would be, of course, the killer feature of AI, if you want. So in a sense, if you think of AI, you often think of these kind of things, right? So really generative capabilities. But lots of its background and lots of applications are still predictive, right? So, so yeah, that's kind of the current situation in that domain. And super quick on decision making because we are already quite far. Sequential decision making in its classic setup as reinforcement learning or optimal control, like model-based approaches. So they are predictive, right? So this is if you think of it, it's like the supervised learning setup, but you don't have concrete input-output examples, but so to say full sequences of an interaction with an environment. But still, you would kind of predict which is kind of the next step that you want to take. And this would not necessarily be a generative setup. But there are alternatives nowadays how you can make it generative. So for example, sequence modeling. So that means you can use a transformer architecture like decision transformer, for example, to predict, so to say, or generate the trajectories that you want to take in such an environment, right? And the self-attention mechanism could actually give you the credit assignment that you want for long-term dependencies. And you would actually prompt it with your desired reward from the environment. So this is the idea. Unfortunately, this is an approach that in practice is very difficult because it somehow needs to extrapolate beyond the offline training data that you would use for the training of such a procedure. So that means it's kind of still difficult in many applications, similar to the setup that we saw before. So usually the predictive approaches are still better here because they also have this reinforcement learning setup baked in. But what is pretty interesting is that you might also apply language models for this kind of application. So, for example, in the robotic control as use case, so there are quite a few approaches where a language model or a vision language model, so a combination with a vision transformer usually, is used to control a robot, right? So to have actually an embodied agent in the end that you give a construction in natural language, and it kind of translates it into a low-level control of a robot. So this is of course very promising. If this would work, it would make such things much more applicable for instructions, and also of course very generalizable. Right, so this would be a generative approach, so to say, for decision making, if you want. Okay, now final piece is agents. So you might have heard about this quite a bit in the past months or year. So everybody now talks about LLM agents, and there are different capabilities that you want them to do. So, for example, you want them to plan ahead, right? So an LLM could do this to some degree by a decomposition of a complex issue into multiple simple steps, right? And then the simpler steps might be solvable, for example, by a tool, right? So even if a language model would not be able to do forecasting, for example, it could basically call a module that does the forecasting for it, like a classic ML mechanism, for example, or a deep learning approach, whatever, a numerical model that it could use for in such a simple step, right? And reflection and collaboration are also things that are to some degree applicable by means of prompting. So that means it seems that this idea of an autonomous agent comes into reach somehow, but one has to be careful. So the capabilities here are still very limited, right? So like the reasoning capabilities, although one see first quite impressive results, are still relatively limited. So I will come to that in a second in the conclusion. But yeah, so this is kind of the workflow that you might think of, right? So you have an LLM or visual language agent as kind of an orchestrator. It uses a predictive model as tool, so to say. It might use also domain knowledge, for example, via a retrieval augmented generation process. And it could actually control, in the end, even an embodied agent by means of the decision making that we saw, right? And it takes, of course, input from some perception modules, which would again be predictive models like computer vision tools, right? So that means you could think of it like you kind of blend them together with a generative agent doing the orchestration work, and the predictive modules are actually called for specific tasks that are not possible to be done by the language model itself. So as kind of the conclusion then, so when to use what now? So I've give you a few detailed examples that we rushed through, I know, so this was very difficult to get if you don't know it yet. But so to say, as takeaway, so deep learning, especially in its form as foundation models, is definitely the method of choice for unstructured data. Classic machine learning is still used a lot for tabular data, just because of the homogeneous nature of the unstructured world and the heterogeneous nature of the tabular world, right? So that means also for those tabular data, you usually don't have the foundation models handy. So that means you have to model it yourself as data scientist, for example. Generative models allow to create new data, right? So, for example, text, images, and so on. And they can be used in a very generic way, like the prompting that you know from the chatbot. So, this is all pretty cool. But the problem is that predictive models are usually still better for predictive tasks, right? So that means if you were, for example, want to do a demand forecasting and you ask ChatGPT to do it, this is very difficult, right? So even if you would give it some examples and so on, because there is no numerical backbone, if you want, it's not trained with this data, it would usually not be able to come up with good results, right? So that means, unfortunately, many business problems are of predictive numerical nature, so like optimizations, and for those, you need predictive models. So now the way forward, as it looks like at the moment, is you can combine it in a way that in a workflow where the generative model, like an LLM, would be the orchestrator, and it would call the predictive models as tools. So that means you still need them, right? But you might apply them in many different applications in a quite generic way. So I will close with some philosophical thoughts that I mentioned in the beginning, in the middle of the talk a little bit, right? So like the current AI, so state of the art being language models, you could still think of it as it learns statistical patterns and makes predictions, right? I saw this generative AI generating the next words, but it kind of predict what it could be. And this all relies on the statistical patterns that were learned in this huge pre-training going over all of the internet, basically, right? So if you want, it's kind of a compression of the internet. But it doesn't really understand. At least there is no clear sign yet, right? So that means you might actually think of it like a stochastic parrot. That's a term that is often used. So that means it knows everything how it is, right? But it doesn't really understand what is behind. So it has no abstract model, if you want, of the world like a human has. It's a slightly different thing. So this also explains, of course, partly why you still see things that are not completely right, right? So if you ask a language model. Anyway, having such a compression of the internet is, of course, super cool, because what it gives you when it generates new data, it gives you kind of a slight twist of it. So that means it's not exactly a repetition of what we have, but it is a slight twist of the data that is available, and somehow this can be pretty interesting and helpful. So that means, yeah, as I said, you need to understand what a generative model is, what a predictive model is, and to actually know when you apply what. And you actually can look out in the next months or years, I think, for such kind of semi-autonomous workflows where the different approaches are kind of applied. Okay, that's it. There were no questions because I was always talking, but maybe there are some now.
Highly interesting and enlightening presentation. Um, I very. Do you hear me actually, Felix?
I hear you,
Am I
yeah.
aware? Oh, good, good,
I was
good.
just looking if the
Because I
slides are still here, but
no,
yeah.
no, I will. There are some questions, but
Oh,
uh, I will tell you a little bit later. But I just would like to conclude. Thank you very much for giving us hope. And the most of the people thinking about artificial intelligence. Anyway, generative AI is an interesting, slightly twisted mirror of our creations. This gives very much hope. And I would just like to thank you very much for this very enlightening presentation. If I may ask you, because I have this privilege to ask you, as a particle physicist, who you are, how is the combination of your endeavors, your PhD in particle physics and machine learning? how is the combination? How can you see it? That's
Um,
kind of hmm?
Yeah, I mean, in particle physics, so I was basically doing experimental particle physics in a sense that doing analysis of the outcomes of collider experiments. So that means maybe I have to briefly explain what this is. So a collider experiment like the one at CERN or so on, what you do there is you have some small particles like protons or so, and you speed them up almost at the velocity of light, and then you smash them together. And if you smash them together by means of Einstein's famous formula, you can basically create matter out of energy. So and you create some interesting new particles, so to say, and they decay then, and the decay products they are collected in huge detectors. So you measure their momentum, energy, and so on. Make small images out of the trajectories and all of that. And this is lots of information, right? And in the end, you want to classify which particle it was, something like that, right? So that means it's this classic supervised learning approach where you actually use machine learning because you don't have a model to do this classification. And this is what I did in my PhD already. So I used machine learning methods, so neural networks and so on, to do this physics classification, if you want. So I really used it as a tool for the science. And this, I think, is in general one of the most promising applications of machine learning or AI. So you can actually use it to, if you want, supercharge the scientific method, right? So you don't have a model for everything because everything is very complex, but you have lots of data. So and you can actually use the data to come up with some black box models. That is often enough if you just want to know what comes next, right? So this was kind of my way into this field, if you want.
Thank you. Now, thank you for answering this question. And now come the other questions,
I
which
see them.
we
I
get
see
more
them.
and more. You see them all?
Now I
Okay.
see them. I didn't see it before, but the
Ah,
first one I think was
from Jean
quantum
Maurice.
computing. Okay,
Yeah.
quantum computing may be used for deep learning. Quantum computing. uh, okay, it's a very different thing, right? So first of all, it has nothing to do with machine learning in the first place. Um, if quantum computing would be available, I think you could use it. Yes, because there might be machine learning algorithms that could be speed up quite a bit if you would have quantum computing. So that means the answer, I think, to the question directly is yes. So my personal opinion on it is quantum computing will still take some time. And it's not even clear from its theoretical foundations, so decoherence and everything, how good it will really work. So that means, unfortunately, I think if possible at all, it will still take some years. So if you want me to bet, I would say we will rather have some pretty broad AI before we have quantum computing. But yeah, of course, it's worth looking for it. Yeah.
Wonderful.
Okay.
Let's
Next one,
l-
units.
next one. And Cosinati.
Yo. Okay. So a unit, if you want, usually uses convolutions to some degree, or if it's a convolutional unit. The unit is just the architecture having um, convolutions in one direction and transposed ones in the other one, so that you basically um, can do what you want to do in such an autoencoder approach. So that means the two are not a contradiction. So what I meant with it is basically you can use those approaches also in the generative models. So units are, for example, used in diffusion models and so on a lot, and they actually use convolutions under the hood. So you can also do this with transformers to some degree, but yeah, usually, as I said, the inductive bias in convolutions just makes sense. So that means I think the answer to it directly would be both are used, right?
Wonderful. And
Okay.
now? let's go for the next.
Main
But I
limitation.
would like just for the people, there's a question which is a very important question for organization. This comes from our student Juliane. Are some other slides available after? I mean,
Yeah,
in any way, our this video will go online, and this video can be viewed by others who are interested who came later. But are they available later?
yeah, they are available. So I already have them on GitHub, so no problem.
Thank you.
There are no
Let's
secrets
go.
in.
Mhm. So let's go to uh, the
Main
main
limitation.
roadblocks, right? Von of Arvin.
Having an efficient autonomous agent. Yeah, I mean, I think the main limitation here is this understanding piece that I mentioned, right? Um, so let's put it like that. So what a human does is more like if you think of the setup of this model-based reinforcement learning and and these things that I mentioned. So we humans, how we work is we actually have a very abstract model of the world. So how we see the things. The machine learning approaches that we take at the moment are rather brute force in a sense that they want to learn everything from scratch from data. So like model free, if you want, right? So like a reinforcement learning agent basically learns by trying things out, or language models learn by look at all the data that we have and learn the statistical patterns. Um, so which make them very efficient in many cases, but also limit them in a sense of reasoning and so on. So now you might argue, um, so why don't we go ahead and just build in those models, right? So that we humans already have. So the issue is that we don't know how it works, right? So if you would know how it works, you would do that and would have this abstraction. So now we try to learn it from data, and unfortunately, the learning from data is very sample inefficient. So that means you need lots of data to actually learn the same thing. So for example, think of a autonomous driving thing. So for a car to do all the decisions itself in all the different circumstances, you need a huge amount of data. And we humans basically come to a new situation and we generalize from our learnings from a very different situation in the past, right? And this is unfortunately not yet possible. So it's more like a generic roadblock than specifically for autonomous agents, but I think you could actually put autonomous agents synonymous with AI. Yeah.
Great. Thank you very much for this question and for answering this question and for the question as well, Avrin. And let's go to the next one.
One of the drawbacks, hallucinations, the techniques which mitigate it. Yeah, I mean, yeah, of course, hallucinations is the thing that I mentioned. So it comes also a little bit from the fact. So both it comes from the fact that there is no genuine understanding, and the other one is of course that we do a compression, right? So that means some things might be lost on the way. So how to mitigate it? So for the second one, so the first one, unfortunately, is the challenge that I just explained, right? The understanding. The second one is something that you can actually mitigate. So, for example, this the retrieval augmentation, right? So that basically you take you load in context of an LLM. So in the prompt, if you want, in the context, you load, for example, some factual knowledge. So like the contents of a book or some specific article or something like that, right? So basically, when you do a prompt, you search for some content that is similar to that prompt, and then you load this content. You load this in the context, right? So you basically look for an article that sounds similar like your question, and then you load those article in the context so that the LLM can actually do self-attention over it. So this is one example. You can not only do this with text, You can also do this with knowledge graphs or whatever, right? So this RAG approach is one way to mitigate hallucinations. Another one, of course, would be fine tuning, but this is more heavyweight. Yeah.
Great. Thank you very much again. And another question of Mr. Oki-Wan Kenobi. Um, I love the name. What about pins?
Okay. Yeah. I mean, this is, I think, in general, one of the things that are very similar to what I explained a little bit, or what I touched with the convolutional neural networks, right? So if you know, for example, the rules of the game to some degree, right? So if you know locality in our physical world for images and everything, right? So you can use it. So that means if you can bake in some inductive bias in the model that you already know, this is of course great, because this helps you to overcome a little bit this limitation in terms of the model, of the lacking model of the world that you have. So if you want, this is just a way to include some of the information that we have into the model itself. So that means, yes, it is promising, but the difficulty is many of the things that we actually deal with in intelligence are not necessarily physics laws, right? So we humans think in a very abstract way, and not all of it is can be solved with a differential equation and so on, right? So that means I fear that reality is much more complex, or is too complex to really put it in simple formulas, unfortunately. Yeah.
Thank you.
Okay.
And shall we go on with Mr. Oki-Wan Kenobi? Are you okay? Do you need a bottle of water or something?
No, no, that's good. That's good.
Good, let's go.
Very nice comment from
Mhm.
Juliana. Okay.
Yes, yes. Okay, let's bring the niceness.
No, no, all good, all good. Okay.
Gen AI with an RLP accent.
Yo.
Sweet.
Okay.
Let's go.
So then,
Hmm.
so could you imagine to have in future a kind of expert system, LLM as a machine that present dedicated? Yeah, if you want this, this is what I meant, right? So I mean, expert systems classically mean if this kind of rule based approaches where you want to basically write down a rule for each corner case. I think this is probably not the way to go. I think the general way of machine learning, so learning from data, I think is much more promising because it's just more generalizable. So going back to the old expert system world, I think will not work. But I think you mean it differently. So it's more like you use some specific machine learning tools for specific circumstances. So this is what I meant. Yeah. Hopefully this answers your question. I'm not completely sure.
Thank you, Oki-Wan Kenobi.
If
Oh, sorry.
no, I was
Want to
just
get back to
reading.
this? Ah, okay. Well, let's go. From SJ.
Okay, I think this is
No.
together with the next one, right? So, or with the next two.
So
Yeah,
shall I?
yeah. Okay, I think what you mean is if you don't use RAG, you can still use some specific prompting scheme to overcome hallucinations or whatever. Yeah, I mean the prompting schemes. So this is of course something that is very interesting, right? So chain of thought or whatever it is. So you can also combine it to some degree with retrieval augmentation, so that you could basically load, for example, old logs from successful trials or so over the course of a of such a chain of thought process. So this is kind of this reflection thing that I mentioned in the agent ideas. So yes, I think both of them are not contradictory but playing together, right? It's not the one or the other. So the REC approach is really simply you load additional context into the prompt if you want. And of course, you can do this in a multi-step approach by prompting one after the other. So I think, yeah, I think you can combine them. There's no reason why this wouldn't work, I think.
So, thank you so much. I think that was it. So, maybe we give a little time for more questions because questions are wonderful, aren't they? Um, and your answers, of course, Felix. Thank you very much for those. I would like to thank you very much, Felix, for your wonderful presentation, for answering all those answers, for giving hope to people who are who are afraid that artificial intelligence could take over the rule. It's still a part of us. I mean, it depends on what we did, but let's leave this out. I would just like to tell you again, we have every month two webinars. The next webinar will be on the 30th of October, held by held on the topic future of data science jobs, analyzing market trends through LinkedIn, Indeed, and beyond. 12 o'clock, 30th of October. You're all heartily welcome. In any way, you're very welcome to come to us. Book a meeting with us on datascientist.com. We are Data Scientist and especially Data Scientist Germany. Thank you for taking part. And thank you very much, Felix, for your insightful presentation.
Thank you
Thank you
for all
very
the
much.
questions. Okay,
Goodbye. Thanks.
goodbye.